Okay, so here we are in section 2.6. Now, just a reminder, there's a lot of examples here in section 2.6. Not a lot of new material. The only really new content was the vertical line test, which we talked about last time. So I am going to do a couple of select examples. We did one of them at the very end of yesterday's lecture, and so I'm going to do the other one, the other selected example today. So it has to do with a bicycle. This is a scenario to describe something that I think we've all seen probably. That when it's dark out and the street lamps are on, and someone's riding down the street in a bicycle, the street lamp light catches the reflector on the bicycle wheel, and it makes this little kind of jagged. Y'all know what I'm talking about. People tend to look at that and think, oh, that's probably a sine wave. But it's not exactly a sine wave. So what is that curve? The path that's traced by the reflecting reflector on a bicycle wheel. And it turns out this is a hard curve to write an equation for, but it's a pretty easy curve to parameterize as it happens. So here's the scenario that we're gonna consider. Here is the wheel. The tire, I guess I'll say the tire of the wheel, and the radius of the wheel is 16. That's given in the statement of the problem. We'll see in a moment. The reflector is on one of the spokes halfway between the axle and the tire. Right, so it's only 8 inches away from the axle. And the idea is, okay, all right, so we're the bicycle's going that way, and as the bicycle starts to move, well, this reflector, on the one hand, the wheel's moving to the right, but on the other hand, it's starting to rotate kind of like that, and the combination of these effects is something vaguely like that. Okay, so how can we make that precise? So what we're going to do is we're going to use one of the strategies that we saw in the section on parameterization, one of the tools in our toolbox, right? Which is to take a certain kind of a movement and break it down as a sum of simpler vectors, right? So I'm going to understand that reflector as the sum of the axle's position. Now the axle is doing a very simple thing. Right, the rotation's got nothing to do with what the axle is. The axle's just moving straight line, constant speed down the road. Okay, so that'll be easy to parameterize. And then on top of that axle, we're going to add this vector here. This vector that always has the same magnitude. That vector's always got magnitude 8. And the only thing is that vector, if I were to draw a separate axis system over here just for convenience, keep from messing up my picture, that vector simply goes around in a circle. Right? So the blue vector is going to be easy to understand. This red vector independently, right, is going to be easy to understand. And then we just add blue plus red, and that'll give us the path of the reflector. Okay. All right, so let's take these one at a time. Let's start with the axle itself. The way to approach the axle. Real quick, let's go back to the statement of the question here. You can see here that the tire has radius 16, right, and the reflector is exactly half the way from the axle to the tire, right? So there's all the premises. Okay, so here was our tire at the very beginning, at the initial moment. Time equals 0. Okay, now here is the tire a little bit later, and you can see it's rotated, right? I've got it. The indication of the rotation is that the reflector has already kind of moved down. It's moved down a little bit. It's also moved to the right, but not as much as you think, because the rotation's taking it back to the left, and it's kind of hard if you think about it all together. Okay, all right. Well, if this has rotated, it is further true that point that was the initial touch point has also rotated. All right, and now I'm going to make a simple but key observation about how wheels work. that's going to allow us to get our hands on the problem here, and that is that when you have a wheel rolling down the road, the amount of rubber that has touched the road is the same as the amount of road that has touched the rubber. Again, I like saying it like that because it sounds kind of deep or something, right? But it's a very simple observation about that. Just means the wheel isn't slipping. Right, so the amount of road that's touched rubber is equal to the amount of rubber that's touched road. And so right off the bat, then I can tell you where that axle is now. The axle in this scenario, if the wheel is rotated by an angle theta, then so that angle is theta, this angle is theta, and very conveniently then the amount of rubber that has touched road is 16 theta. Right, so flashback to a geometry class from high school. The length of an arc on a circle is the radius times the angle. Okay, so that's 16 theta, and that means that this distance is also 16 theta. That means that that distance is 16 theta. The axle has moved 16 theta down the road. And so the position of the axle, again, real easy to write down. The y-coordinate of the axle is always 16. After all, the radius of the wheel is 16. Right? The x-coordinate of the axle, we just saw 16 theta. And so we are, that's the wrong color, isn't it? We are halfway done. There's the position of the axle. Everybody good? How we doing? Everybody happy? Okay. All right, so next part of the question. I am now going to be interested in this red vector here. Right, so ultimately what I'm interested in is the position vector of the reflector. I'm interested in x ultimately, right? But the axle at A is something I already understand. And what's going to be easy to write down is not x, but x minus A. This red vector is x minus A. Let me get this out of the way. So that vector, x minus A, is the thing that's kind of going around in a circle like that due to the rotation of the wheel. Okay, is everybody on board? So let's do it. This rotation, okay, well, the rotation, you can see here this vector has a fixed magnitude of 8, right? And it is rotating the same way that the wheel is, right? So that angle there is this same theta that we referred to here. And so now it's just a matter of, flashback to trig class from high school. And now the theta is kind of going what you might call in the backwards direction, the negative, the opposite of the polar direction, if you will, right? So not hard to persuade yourself that this magnitude of 8 is multiplied by cosine theta and then negative sine theta to give me x minus A. How are we doing? Everybody follow the reasoning there? By the way, if you're a little shaky on your trig, now's the time to polish that off. Trig is assumed in this class, and it unavoidably comes up a lot. Again, the world is full of circles, so this is not going away. All right. Okay, so it's all over but the shouting at this point. We have x minus A. We have A, and then therefore the position of the reflector x is just the sum of these two, which we have written down right there. And here it is again: axle plus what you might call relative position of the reflector. Okay. All right, so pretty weird little formula we have here. Right? And again, try to find y as a function of x in a convenient way. It's harder than it looks. Right? So it'd be pretty hard to write down the equation of this curve, but it is no sweat to write down a parameterization. Okay. All right, so there is a homework exercise assigned that is what I'll call more fun and games with bicycle reflectors. So it's going to take what we've done here, this strategy of writing the position of the reflector as a sum of component piece vectors, whatever you want to call it, right? But writing out the vector as a sum of simpler vectors and just understanding those individual simpler vecters and adding. Okay, so again, more examples in this section. I'm going to let you all read those on your own. Wanted y'all to have access to a bunch of examples. I'm going to move on and talk about limits in the next section now. This is multivariable calculus. Y'all have all had single variable calculus. Y'all all recall that derivatives are defined ultimately with limits. Okay? You may also recall that integrals, if you really write down the definition, is defined with limits. Okay? So the limit is the fundamental cornerstone idea of calculus. So kind of a big deal. Right? And yet, it is awkward, surprisingly awkward, to actually define limits correctly without coming up with nonsensical ideas about infinitesimal numbers and sketchy stuff like this. Right? So, interestingly, historical note, it was a very, very long time after Newton and Leibniz started pursuing the ideas of calculus, before anyone actually really wrote down a good, effective, not nonsensical definition of a limit. And that's kind of a jaw dropper, just a historical note. The most important idea in calculus, most fundamental idea in calculus, and no one really nailed the definition for like 150 years. It's very interesting, I think. And it's because it's hard. It's a hard definition to write down. Here it is. And some of y'all may have seen this before. I don't want to spend too much time on this. We're not going to turn this into let's prove things with the definition of limits class. That would be beyond what Math 212 can reasonably do. But I do want y'all to have a reasonable sense of what the definition says, so that, because there's a lot of bad notions of limit out there that are really unrepresentative and problematic, and can lead you in bad directions. So anyway, here's the idea. I like this phrase down here. For a limit to exist and equal a value L, what we need is for the function to get arbitrarily close to that value L, as long as x is sufficiently close to the given input value A. So arbitrarily close and sufficiently close. Let me talk through how that relates to the definition. And come up here to this picture real quick. In fact, let me zoom in one notch. Here we go. Okay, so we have this value L there that we assert is the limit as you approach this value A in the domain. You all know what that picture looks like. It's like the function is, let me remind you of a bad notion of limit. It just gets closer and closer and closer. Right? What does that mean? Okay. So arbitrarily close. Arbitrarily close says, hey, listen, no matter how close you require that the function get to this value L, arbitrarily, right? No matter how close you get. Now let's hit the pause button. How would I represent a function and being close in some sense to the value L? And we say that a value is close by defining an interval around L. The interval we're going to say has radius epsilon. And well, we can say that a value of the function is that close. It is within epsilon of L by just saying absolute value of f of x minus L needs to be less than epsilon. So arbitrarily close, going back here to the definition, arbitrarily close to the value L, we represent that by saying, look, no matter what epsilon you come to me with, I don't care how small epsilon is, we're going to have a punchline of this discussion that says, yes, we can create a set of circumstances where the value of the function is no more than that far away. In other words, at least that close to the value L. So that's the arbitrarily close part. Okay. Okay, what about this next part? When x gets sufficiently close to A. What do we mean by sufficiently close? Well, we need to be able to say, look, obviously the function's not going to do what we want it to, over here on the y-axis for all values, right? But as long as x is sufficiently close, as long as x is within a certain yet to be determined distance away from A, we're going to call that distance. Color choices. We're going to call that distance. Sorry, I'll put this in pencil. Delta, right? And I can say what it means for a value x to be within delta of A by requiring simply that the absolute value of x minus A be less than delta. So when we say, I want the function to get arbitrarily close to L. There we go, in yellow, arbitrarily close. No matter how close you want me to get, we're going to get that close. As long as x is sufficiently close, I need for there to be some notion of close appropriate to the choice of epsilon. So there needs to exist some delta such that if x is that sufficiently close to A, that I get my desired punchline that f of x is, as required, appropriately close to epsilon, to L. Okay, so so that's the idea. I think you can see how this conjures the image that we want. In other words, what we need. Forget about definitions, forget about wording and details. This idea that no matter how close you require that we get to that value L, we can make sure that happens. All we've got to do is make sure that x is appropriately close to A. That this conjures the picture that we want, namely that the function is, now let me go back to, what I heard in high school more than I should have, that the function's just getting closer and closer and closer, and man, it just keeps getting closer, right? So this is a precise way of saying it. You'll notice that in this definition, there's no reference to infinitesimally small numbers or other fanciful concepts that don't actually make any sense. Right? And yet, it gets our hands on kind of that same idea. So this is a wonderfully elegant way to approach this problem. We get at a mysterious and critically important concept by simply making clever choices about which number gets picked first, which number gets picked second, and then what do you require of the input point and the output point accordingly. Okay, one other quick detail that I've got to hit before we go on, and that is, let's look at this picture again. Why are we interested in the value of the limit? I ask rhetorically. I use red, so this value here. Why are we interested in that value of that limit? Why don't we just say f of A? The reason we're interested in the value of that limit is because we know, and we've seen this happen before, that sometimes we're interested in this function and it's all perfectly well defined and everything's fine and dandy right up until you get to that point A, and at that point A, the function's just not defined. This is what motivated our desire to define limits in the first place. Look at the definition of a derivative. You can't let h equal 0. You need h to get as close as possible to 0, but it's not allowed to actually be 0. Okay, so let me say that in this context. When you're defining a limit, you'd better not make the definition of a limit make any reference to the value of the function at A. If the definition of a limit requires that f of A be defined, then you can't use it in a context where f of A is not defined. And that's the context we need it to be defined in, right? So, very importantly now, from what I talked through moments ago, I'm going to have to adjust our definition just a little bit. I need to absolve us of any responsibility of what's happening when x is equal to a. I need my definition to stand back and say, look, when x is equal to a, don't worry about it, no problem. We don't care about that for this definition. And where that comes up is right here. Right there, you can see we're saying, look, it's only when x minus a is greater than 0. In other words, it's only when x is not equal to a that I need, a certain thing to happen. I have responsibilities when x is not equal to a. But if x is equal to a, if this difference is 0, all bets are off. This condition's not satisfied, and I don't have any responsibilities over here. Okay. All right, so that's why this is here, right there. One last quick comment. And by the way, I know that the presentation y'all have seen on single variable limits, widely varied. I'll say that. Some people have never seen this definition before. Some people have seen it, and it's been kind of, in passing. And maybe, perhaps, some of you all have seen thorough treatments of this, I suppose. Okay. But one thing I want to make sure everyone is aware of in single variable calculus, and the same will be true in multivariable, because of this, when you see this expression, limit as x approaches a, very, very importantly, because of that, you may always assume that for the purposes of the computation of that limit, x is not equal to a. Right? So it's never equal to a. And where this tends to come up is if you find yourself dividing by x minus a, that's a situation, we're dividing by something? If we're dividing by something, what if it's 0? If it's 0, we've got big problems, oh no. Right? Not here, you don't. If you're taking a limit as x approaches a, x minus a is never 0. And you may divide by it at your leisure. Okay, alright, so enough of that. Okay, so real quick then, again, here's our picture. Here's the picture that we draw to think about the epsilon delta definition of limit. Notice that I have drawn a graph. And I've spent a bunch of time, I'll say, trashing the concept of graphs recently. Certainly as a context, it's not something you want to cling to, right? So let me now separate this picture into its pieces. On the one hand, there's the x-axis, and there's stuff that's happening on the x-axis. There's the point A. There's the interval of radius delta. There's this chosen value of x somewhere in there. There's a bunch of stuff happening on the x-axis. Oh, I guess I'll... A bunch of stuff happening on the x-axis, and likewise, there's a bunch of stuff happening on the y-axis. Right? Everything that happens in this definition, all of these items, epsilon, delta, x, a, f of x, L, all that stuff happens, or is used on, is represented in one of the two of these axes. Okay? So even though it's convenient and familiar and comforting to think about, what's going on with the definition of a limit in this graph context, it is absolutely not necessary. And you are perfectly welcome, and in fact we are going to need to reinterpret this with these axes drawn separately. So this is not a graph, right? I'm not drawing a graph. I'm drawing my domain on one side, and I'm drawing my target on the other side. And notice it's dimensionally simpler. Up here I'm doing single variable calculus, but I'm already wastefully spending all of my paper dimensions, just all two of them, even though it's technically a single variable function, right? Whereas here I'm being a little bit more dimensionally frugal, I like to say, and one-dimensional picture for a one-dimensional function. Okay. All right. Okay, so with that in mind, here's the generalization. I think this is an easy buy. So what is the analog of a one-dimensional domain with, we're looking at a point, we're looking at a radius, and we're looking at another point that's within that radius. The two-dimensional version of that, if I had a function with two input variables, in other words. Okay, well, we have a point and we have a radius. Still going to call the radius delta. And that radius defines, well, not an interval, but it defines a disk. And then this point that is within that radius, x, is just something that looks like that. Okay? And I can describe all of this totally analogously to how I did in the one-dimensional case by that difference vector, x minus a. I can't say I need that to be less than delta because it's a vector. Vectors aren't less than numbers, right? You can't compare things like that, right? But what I can say, what describes x being in that disk is that x minus a have magnitude less than delta, right? So that's the only thing that has to change when you want to write the definition of a multivariable limit. Look how very, very similar this definition looks to the one on the previous page. It's got the same notion of arbitrarily close, sufficiently close. Epsilons and deltas and all that's pretty much the same. Greater than or equal to 0. X is not equal to a. All that stuff's the same. The only difference is that it's a magnitude of x minus a as a vector instead of absolute value of x minus a as scalars. Everything else is exactly the same. Okay, so this is the definition of a multivariable limit, and I think it's important for everybody to see that that is what it is, and to know where the idea comes from. Again, it being, after all, the fundamental concept of all of calculus, if you want to look at it that way. Okay. All right, so now I'm going to move on to more computational stuff. How do we compute limits? It's another tools in your toolbox kind of a situation. There is no single algorithmic, here do this, turn the crank, out comes the answer, kind of a deal. Certain scenarios, you get lucky, certain things happen you can capitalize on. Here's one. Suppose that you are looking at a limit as x vector, so x comma y, approaches the origin. And I'll make the observation that if you're approaching the origin, and let's look at this right there, if you're approaching the origin, magnitude of x minus a becomes magnitude of x minus 0, which, by the way, becomes just the polar coordinate r. Right? And if you think about that, if you replace this with just r, or if you prefer absolute value of r, then this becomes kind of a single variable limit again. Let's not sweat the details, but I think that's a plausible analogy at a minimum. And it is not hard to show, in fact, along the lines of this reasoning, that if you're taking a multivariable limit as you approach the origin in the xy plane, that is equivalent to a single variable limit where the polar coordinate r approaches 0. Okay, now this is a peculiarity of the origin. This only works at the origin. Roughly speaking, the point here is that the origin is the only point in the entire xy plane with a unique r value, right? It's the only point with r equal to 0. There's lots of points with r equals 6. So this argument doesn't work when r equals 6. Some point where r equals 6, that just doesn't work. Only for the origin. Okay. So that being said, all you got to do in this case that you're approaching the origin is, if you want to replace everywhere you have an x, just put r cosine theta. Everywhere you have a y, just put r sine theta. And take the polar limit as the scalar r approaches 0, and you can just deal with your multivariable limit as a single variable limit. And sometimes this is actually even useful. So not always. Again, this is the tools in the toolbox that won't always give you something you can deal with. But here's a great example where it does. How would I compute this multivariable limit? Now you got to beware. You cannot use single variable calculus techniques on this. This is not a single variable limit as written. Right? This is a hard problem based on the tools that we have to work with so far. I mean, do I have to plug into the epsilon delta definition? I certainly hope not. That'd be hard, right? Okay, well, we are approaching the origin. So I'm going to just replace the limit as r approaches 0. Everywhere I have an x, I'm going to put r cosine theta. Everywhere I have a y, I'm going to put r sine theta. Just plug that all on in there. And I get this great big expression. Lucky break, look what happens in the denominator. I have a Pythagorean identity. Sine squared plus cosine squared is 1. Common factors of r, various places, grouped them all together, simplify. So I've done some significant algebra there. Make sure to fill in those blanks. But the punchline is that breaks down to this, what I'm going to call single variable limit. Okay, how are we doing? Is everybody good so far? We're not done yet. I do have to finish this off, but is everybody on board so far? So what do I do with this limit? Now, here's the problem as it remains. I'm letting r approach 0. What's theta doing? Well, here's the thing. R is approaching 0 in the sense that, these disks are getting smaller and smaller, so I know r is approaching 0. But theta, I haven't got the slightest idea what theta is doing. We don't know if theta is doing something convenient. Theta is not necessarily a constant, right? How do you know we're not approaching the origin in a spiral, right? Theta is just running to infinity. Or maybe theta is constant. Maybe theta is kind of bending it in along a curve or something. We don't know. Okay, so at a glance, you cannot just look at this expression and say, you know what, I'm just going to kind of pretend that the theta stuff is, I'll drag it along for the ride, but I'm going to pretty much treat it as a constant and just deal with the r stuff. You can't do that. We don't know theta is constant. So, problem. Okay. So this is where you get stuck in a lot of cases. This is where the argument becomes useless in a lot of cases. Okay. But not this one. What is nice about this one is that this business over here with the thetas in it, I don't know what theta is doing. I can't control theta. But I can control this expression. That expression right there is definitely between 1 and negative 1. Because it's trig. Sine and cosine. I'm not dividing by anything, right? There's no secants in there or tangents or anything like that. So that is a bounded expression. So now let's look back at our actual deal. R is approaching 0. We're looking at r cubed, r cubed is clearly approaching 0. That r cubed is being multiplied by something, but it's being multiplied by something that's bounded. And now I appeal to your algebraic intuition. If you have something approaching 0, and you multiply it by something that just can't get big, I don't really care how much that theta business might be wiggling. It can wiggle all it wants, but it's getting multiplied by something approaching 0. So that limit's going to be 0. Everybody on board? Okay. So critical to this working is that leftover business is bounded. Okay. Anyway, we've computed a multivariable limit. Again, tool for your toolbox. Does not always work. Again, it only is applicable when you're approaching the origin. The trig has to, we got pretty lucky in how this potential unpleasantness simplified so nicely, right? Sine squared plus cosine squared. So, nevertheless, every so often this works. Okay, so I want to talk about a misinterpretation that students very often make about multivariable limits. And let me just go straight to the picture. Students tend to think, look, I'm approaching some point A. And if I'm approaching A, I'm going to be approaching along some line, let's say, that line is defined by some direction vector, u, and then let's look at a multiple of that direction vector, tu, and I ask, what would happen? How about I just write down a plus tu? A plus tu would be there, and if I want x to approach a, I just need t to approach 0. Right? I mean, x minus a is tu. If t approaches 0, x approaches a. So why can't I just write this? Why can't I just write a plus tu? That's the x that I'm plugging in. We'll just let this t approach 0 and check it out. My multivariable limit, I've rewritten it again as a single variable limit. Isn't that nice? And why can't I just use this definition? Now, granted, I can't just pick a single unit vector, u. I've got to consider all possible unit vectors, because after all, I could be approaching from any direction. So if I append here that yes, for all unit vectors, if I always get the same value of the limit L, no matter which unit vector I pick, shouldn't that be good enough? Doesn't that say I'm going to approach from every possible direction? And as I approach from every possible direction, if I always get the same value L here, I mean, come on. I mean, doesn't the limit have to be that value L? You can probably detect from my tone that I'm, the answer is no. So the answer to this question is no. This candidate, this hopeful alternative point of view on limits is wrong. And it's going to sound weird to say it, but the reason what this does not account for, it does not account for the possibility that we might be approaching A along a curve. And believe it or not, that makes a difference. It's very counterintuitive. Students tend to think, look, if you're approaching along a curve, okay, at that moment that you hit A, what direction are you coming from? And shouldn't the limit along that purple curve always necessarily be equal to the limit along that red curve? And the answer is no, it just isn't. Some functions are weird. Multivariable functions have in the domain with this extra full dimension, and there's two full dimensions in the domain of this function. There's a room for the independent variable to wiggle around in ways that you've never seen before, because in single variable functions there is no two dimensions. In single variable functions there's just the one. So there are anomalous oddities afoot that are brand new, that you've never seen before. And I want to show you one of them. Now this is a weird function I'm about to write down, but I think it's a convenient way to get at the idea that we're looking at here. So here it is. It's the absolute value. It's the magnitude of a vector divided by the angle of the vector. And so let's just look at this for a moment. This is, let me zoom. This function here seems pretty straightforward. You give me some vector x other than the origin, not the origin. The origin doesn't have a well-defined angle, right? But other than the origin, magnitude is perfectly well-defined, angle is perfectly well-defined. You could divide them. That's a problem. Perfectly well-defined function. Minor detail we have to talk about. I want to make sure that I'm not dividing by 0. So on the positive part of the x-axis itself, we're going to pick 2 pi instead of 0 for the angle, and then that angle is never 0. We're never dividing by 0. Everybody on board? Cool. So, well-defined function. All right, now doesn't even seem that strange. It's hard to draw a picture of this function, but anyway, let's just kind of think about it a little bit. In particular, I want to look at the limit as I approach the origin. Now, of course, the function's not defined at the origin. No problem. We're not responsible for it being defined at the origin. We're approaching the origin. Okay, so let's consider this limit, and let's consider the naive, the along straight lines. The definition that I'm claiming is no good. Let's take this naive approach and see what our analysis is of this limit. Well, along straight lines, look, here it is. Straight lines are parameterized like this. There's that a plus tu. A is the origin. Right, so 0 plus tu. We'll plug in tu into our function. The function is, again, magnitude divided by angle. And now, let's think about this. So this is a straight line. Because this is a straight line, this theta is a constant along that straight line. That's because it's a straight line, right? And that means as you're approaching the origin, well, that angle is just always the same. So we have a constant in the denominator, and now let's look at what's left over. T is approaching 0, and there's a factor of t in the numerator, and I think it's uncontroversial that therefore this limit is 0. All right. Now we have now considered for all possible straight lines, right, no matter what that u vector is, we have considered all possible straight lines, and for each and every one of those straight lines, we get an answer of 0 every single time from every possible straight line direction that you might approach the origin. Always get the same answer. And so this naive attempt at understanding multivariable limits would have us believe that the answer to this question is that the limit exists and that the value is 0. And I think this is pretty persuasive. It's pretty tempting. Right? Now let me try to convince you that this is impossibly wrong. Right? Impossibly wrong. And here's why. I'm just going to consider a different path. Let me draw a picture here. Here's my domain. Here's the origin that we're approaching. And let me consider this curve here. This is a spiral. It's hard to draw very well, but this is the spiral, r equals theta. And you know what? Technically, I really shouldn't go past the. Here, I'm sorry. Let me do that. So r equals theta. In other words, absolute value of x, magnitude of x, I should say, equals theta of x. Right. So as theta increases, we start off with low values of theta, but increasing. We have small values of r, but increasing. And as theta increases, I get further and further away, and it spirals out away from the origin. So that's what this curve looks like. And what do you suppose happens if we take the limit along that line? Well, along that line, I'll just write it out here. The limit along this blue line the limit of the function, well, the function is absolute magnitude of x divided by theta of x, which according to this right here is always equal to 1. So I'm taking a limit of a constant 1, which is 1. And this is absolutely unacceptably contradictory. Right? So along every straight line path, we get come on, pen. Along every straight line path, I get 0. But along this spiral, I get a non-zero. So we have, in some sort of a weird way, some sort of mysterious way, we have one of these kind of discontinuities here, where you come from one direction, you get one value, you come from another direction, you get a different value. This is in single variable calculus what you'd call a jump discontinuity. This limit cannot exist. I mean, come on, there's no way you could say the limit exists here reasonably. Right? So this point of view of, let's just look along the straight lines completely misses this problem. You can't do it. Everybody on board? Okay. All right. All right, so it's a very disturbing example, by the way. If you're curious what this function looks like, by the way, it's not something I can do here in class. But if you come to office hours, I can fashion a sort of a three-dimensional model of the graph of this function, and I can sort of give you a little bit of a hand-waving kind of geometric idea of why this is true. But it doesn't work in a large classroom setting. So anyway, come by my office hours if you're curious. Okay, so. Is there an alternative interpretation that we can use? And yes, there is. Here it is. If you want to talk about a multivariable limit, the alternative is to consider not just the straight line paths, but all continuous paths that go to the point in question. So, same idea. You can break down a multivariable limit into a statement about, well, just check paths. But it's got to be all possible paths. And that's the bad news, right? There's too many possible paths. You can't ever check all of them, sort of brute force. So let's approach the origin here. Okay, well, there's straight lines, right? There's what you might call parabolic paths. There's spirals. But there's also knuckleballs, right? And there's, indecisive spirals. Right? I mean, you can't enumerate all the possible paths. There's way too many. Right? So, one of the important takeaways of this alternative point of view of the definition is that even though this is nice and true, it's practically never useful to prove that a limit exists, which is disappointing. But here's what it is useful for. It's wonderfully useful for proving that a limit does not exist. Right? So if I want to show that a limit does not exist, if I want to show that that is not true, all I have to do is show that not all continuous paths give me the same value. Right? If I can show that not all continuous paths give me this, same value L, if there's any sort of contradiction, if you ever find any two paths that give you different values, or if you find one path along which the limit doesn't exist, they're good. Right? And you instantly know the limit could not possibly exist. So that's these two results here. If you find, this is the one that comes up most often, if you find two paths such that along those two paths the limits give you different values, then your limit does not exist. And let's see that in action. Here we go. Here's a multivariable limit. X is approaching the origin. And by the way, you try to use polar coordinates here. Something to think about. I'll just leave that dangling. Let's see what we've got here. We've got to consider all possible paths. Well, no, we're going to consider a finite list of paths and with fingers crossed hope that we get a contradiction so that we can declare that the limit does not exist. Again, that's the only conclusive punchline you can get. Since you can never check all possible paths, since you can never prove that the limit does exist, having the values equal each other, this doesn't help us. This does not get us toward, and we're done, right? It's arguably then kind of bad news. Okay, so here we go on a hunt for contradictions. We're going to consider first, let's see here, along the y-axis. Let's look along the y-axis. Here's our xy plane. If I want to go along the y-axis like that, I can approach along the y-axis with that parameterization. By the way, y-axis. Note, we need a parameterization, right? I'm going to have to take this path. I'm going to have to plug it into the function. I'm going to need to know x and y as functions of a parameter, t, so I can say t approaches 0. So we need parameterization. So this is one of the reasons why we need parameterizations right here. So persuade yourself that this parameterization parameterizes that path as t approaches 0. And in so doing, we're going to take this value of x, plug it right in there for x. We're going to take this formula for y, plug it right in there for y. And out comes, very conveniently as it turns out, because x is 0, we have a factor of 0 there. Our numerator is just 0, and this limit is 0. Along this one path. Now again, I emphasize the argument that we've just given here just works along that one path. Let me quick pause for questions. Is everybody on board with this? While you're thinking about that, make sure you're good with single variable limits. A lot of students are not good with single variable limits. A lot of students will look at this expression right here and think that that is an indeterminate form. After all, isn't it kind of a 0 over 0 kind of thing or something? Right? T is approaching 0. Right? Why isn't this a 0 over 0 indeterminate form? Well, very importantly, I suppose technically it kind of is, but you don't need to view it that way because this actually is 0. This thing here, it's approaching 0, yeah. But very importantly, that denominator is never 0 for the purposes of the limit. Right? So the expression that I am taking a limit of here, this fraction, is 100% 0. We're taking a limit of the constant 0. There's nothing indeterminate about that. Is everybody on board? So again, make sure to brush up on these ideas and think it through, and don't. If you can't, reliably and validly manipulate the resulting single variable limits, then the foundation for you being able to do multivariable limits is shaky. Okay. All right. Okay. Now, do we have a contradiction? Well, we've only checked one path. We're hoping we need to find two paths along which we have a contradiction. I haven't even got one path. I've only got one path. There's no contradiction yet. So let's consider other paths. We're going to check now lines like this. They're all y equals mx. Right? Different values of m. But conveniently, by leaving m as an unset constant, I can check all of these lines simultaneously. One calculation. That's convenient. Okay. So that said, how do we parameterize y equals mx? Well, that's a graph. Graph parameterization. Flashback to the couple of sections back. There's your graph parameterization of that graph. So t comma mt. Okay, now don't forget what we do with the parameterization. The formula there for x goes in there for x. The formula here for y goes in there for y. Plug it all in, and we find ourselves looking at that expression. And now here again, make sure you understand single variable limits. Got to deal with this appropriately. Nice thing that you can do here is notice that there is, in all three of these terms, there's a common factor of t squared. We're going to cancel that common factor of t squared. Now, slow down. Hey, are you allowed to do that? After all, but what if t is equal to 0? you can't cancel 0 over 0. That's not legal. Right? So, are we allowed to cancel the t's? Yes, you are. This says right here, t is never 0 for the purposes of this limit. Right? So, canceling the common factor of t squared is perfectly fine. This constant's all that remains. The limit of a constant is that constant. So, okay. And do we have a contradiction yet? Yes, indeed, we do. Along one path, let me get rid of that. Along one path, we get that value. Along this different path, we get, well, a different value. Two different answers along two different paths. This multivariable limit could not possibly exist. And so, here, let me zoom out. So the multivariable limit that we were looking at does not exist. How we doing? Yep.
Can we just use the TMT to...
Yeah. That's right. Yeah, that was my very next point. Yeah, absolutely. So what he's pointing out here, excellent point, is that in fact we don't even need this calculation here at all in the first place, because you look at this calculation here, and notice we get different answers for different values of m. Right? The whole point of this parameterization t comma mt was that we're parameterizing all different straight lines all at once. Right? And so when m equals 1, you get some value. When m equals 2, you get a different value. There's your contradiction. You don't need this whole separate calculation up here. Right. So I would suggest, by the way, that this be the first thing that you do. The very first thing that you should plug in would be this parameterization. Check all those straight lines, all the straight lines through the origin all at the same time. And if your answer depends on m, if it's anything other than a, independent of m constant, you got yourself a contradiction. Okay. All right. Very importantly, don't stop after checking all the straight lines, right? We talked about that back here. It's simply not good enough to check all the straight lines. Here's a nice example, right? The spiral on this function. Straight lines don't do a good job on understanding that. So here's a different example. It's not a weirdo example like that one was, but let's look at this. Now there's a temptation to try polar coordinates. After all, you are approaching the origin. Polar coordinates would not work well here, because you've got in the denominator x to the 7th, and that's not going to simplify conveniently, and so you're going to have stuff in your denominator, and you're going to have this looming question of how do I know that the trig associated with this is bounded, because how do I know that denominator doesn't approach 0 or something? First, there's some way that theta could move that it'd be a problem, right? So polar is not a good approach here. So we're going to try different approaches. Here's all the straight lines. Limit calculation. I'm going to say bad news. We get 0 along all the straight lines. No contradiction. Contradictions are the only thing that we can sort of hope for that would possibly help us draw an actual conclusion. This is making it look like maybe, possibly, the limit might equal to actually 0, in which case our approach along different lines doesn't prove anything. So that's bad news for us. Okay. All right. Right, so straight lines, you get 0. What about along a parabola? There's a parameterization of a parabola. Notice y equals x squared. That's the graph parameterization of y equals x squared. And again, we get 0, and, no contradiction. I'm going to say check and then frowny face, because, again, we can't, that doesn't allow us to conclude anything. It's increasingly sort of seemingly pointless. We're like, come on, we checked all the straight line directions. We even bent one in, and we keep getting 0. Come on, surely. Right? But check this out. Look along this cubic, where y is equal to x cubed. compute, the answer is not 0. So there's our contradiction, and despite how it was looking initially that, oh my gosh, we keep getting the same answers, surely this limit exists. No, the answer is this limit does not exist because we have ourselves a contradiction. So be it. Everybody on board? All right. Okay, I'm going to go real quick through the next couple of things. They're pretty straightforward. Continuity, I hope you all remember continuity. It's another important idea in calculus. This is a definition of continuity. It looks just like the single variable definition of continuity. A function's continuous at the point A if three things. The limit has to exist. The value of the function at A furthermore has to exist. That's independent of the limit existing. Right? Limits specifically don't make reference to what the function's actually doing at that point. So that's a second requirement. And then the third requirement is that they have to equal to each other. So continuity is a strong condition. This can be useful actually for computing limits. Now let me first walk through the seeming circularity of this. If I want to show that a limit exists, I would need to cite continuity. But how would I prove continuity? In order to prove continuity, I would have to show that the limit exists. So this seems like a chasing our tail kind of a scenario. So if I want to use this to prove that the limit exists, how can I do that if I need to know the limit beforehand? Okay, so anyway, that's the worry. Here's the good news. You don't have to prove it because it's been proved for you. Here is a long list of functions, very long list of functions, that it has already been proved, and you may cite these theorems. Thank you, old mathematicians. All of these functions are continuous, and you can feel free to just capitalize on that. And knowing that the function is continuous, because it's continuous, that tells you the limit exists, and furthermore, that tells you a handy-dandy formula for how to compute that limit. This limit is equal to, well, just plug in. Very nice. Okay. Again, you can only use this as a formula for computing limits if you know the function's continuous. So you've got to actually check that. And let's look at this example here. Let's go through the theorems. All polynomials are continuous. All of them. Cite at your leisure. Trig functions are continuous where they are defined. Now, that's a big stipulation. I mean, y'all know, right, that tangent is got a dramatic discontinuity in it. It is also not defined at that point where there is that dramatic discontinuity. But where it's defined, if you take some value of tangent, where tangent is defined, continuous. Right? So likewise, logarithms, where they're defined, they're not always defined, right? Negative values, 0, not defined, right? But other than that, continuous. Et cetera, et cetera, et cetera. Exponentials, rational functions are all continuous where they're defined. Again, that's a huge list. Even better than that, if you have two continuous functions, the sum is continuous. The product is continuous. A scalar multiple is continuous. The quotient's continuous. Be careful. That's as long as the denominator is not 0. Obviously, that'd be silly. Right? Okay. So, for example, then, let's look at that function. Let's show that this function. Let's compute this limit. I'm going to compute this limit by plugging in. How do I know that I can plug in? I'm going to show that this function's continuous. Well, the numerator is a polynomial. Continuous. This denominator has in it a polynomial. It also has in it an exponential. And the sum of two known continuous functions is known to be continuous. So So that denominator is continuous. Then I can cite and say, if the numerator is continuous, which we just observed that it is, if the denominator is continuous, which we just observed that it is, then this fraction is continuous. And so, plug in. It's just an arithmetic calculation to compute that limit. Yep.
Does that include, I guess, functions that don't pass the vertical line test, like y squared, for example? Or could you...
What do you mean? So I don't know what you mean by y squared.
So for example, like y squared was the numerator, right? Would that be...
If y squared was what?
Was the numerator of that limit, right?
So if this, if this up here were y squared?
Right. Could you say that y squared, like...
But so this is a polynomial and it's definitely continuous. I just don't know what you mean by doesn't pass the vertical line test.
In terms of like a like it's kind of like that,
So you're thinking of the graph.
Right.
I'm thinking of the function.
Okay.
So you stepped on the same landmine that so many students have stepped on that kind of a landmine before. So the devil's in the details, and you got to think carefully about, what is the domain of this function that we're talking about? This function is defined where x, y, and z are all independent variables. Right? So y is not an output value, and you're thinking like a sideways parabola or something. That's got nothing to do with this function. But that's a great question, and thank you for asking that. Yeah. Okay. Lastly, and just to throw it out there, this is highly believable, but if you have a function that has multiple output values, a vector-valued function, we call them. Very convenient terminology. It's easier to say vector-valued function than it is to say function whose target is Rm, where m is greater than 1. Right? Okay. So vector-valued function. The limit of the vector-valued function is the vector of the individual limits. In other words, you can compute limits component-wise, we call it. One component at a time. I think that's pretty believable. And then the last observation that I want to make is that if you have two continuous functions, f and g both continuous, then their composition is also continuous. So adding to the list of things you can do to continuous functions and recover continuous functions. Okay. Let y'all read the rest of the section. I'm going to move along now to linear algebra. I know we only have a few minutes left, but we're behind schedule, so we got to do everything we can to catch up. So linear algebra is a separate course, right? Brings up the question of why we're talking about a little bit of linear algebra here in Math 212. And the answer is, it turns out it's just crazy handy. You can do things with multivariable calculus. If you have the language of linear algebra to work with, you can do things that you just couldn't do it otherwise. This is very, very convenient. Here's another bit of evidence for you. Why is it that important? It's so important that if you look at what math majors take, not that you have to take those courses. Here we are in Math 212, perfectly fine. But the kind of the math major sequence is to take the full course in linear algebra first. You take Math 221 first, and then after that you take Math 222, which is a multivariable calculus course where they capitalize big time on all that linear algebra that they learned in 221. So we're not going to do all of that. We're not going to do all of Math 221 by quite a bit. We're going to dip our toe in that ocean, just a teensy-weensy little bit. It turns out that with just a little bit of linear algebra, you can do a lot of great things. Okay. First thing I want to talk about is how are we going to describe derivatives? And I know that's the next chapter. But let's just kind of, think back to single variable calculus. Right? How do you define the derivative? Well, it's a limit. Force a habit. X approaches H approaches 0 of f of x plus h minus f of x over h. And I'm sure you'll all remember this. Let's try to define a multivariable derivative now, and I don't know. For lack of a better idea, let's try to steal let's try to, rip off from the single variable context, and with fingers crossed, let's write down, hopefully, that f prime, I guess. I don't know, I'm going to put a question mark there. Not sure what that's going to mean, but of x. Now, wait a second. Now, this is a function defined on a multivariable domain, so f is computed at a vector x. And I ask, can we define the derivative, or whatever, as a limit of f of x vector plus h vector minus f of x vector over h vector, and then have h go to 0. Now, of course, h, being as it must be a vector because we're adding it to what is unavoidably a vector, h is a vector. It's approaching the origin vector, and this is a multivariable limit. So it would have to be anyway. Right? So how about it? Is this a reasonable thing to write down? Can we just write that down and call that our definition, and off we go? And the answer is no, you can't. This doesn't make any sense at all, because check it out, we are dividing by a vector. I don't know if y'all noticed when we were defining vector algebra, we never quite got around to defining division of vectors. It's because there is no division of vectors. There does not exist an algebraic operation that you could call division and that would reasonably behave like a division ought to behave for vectors. So this whole concept right here, it's a non-starter. It just doesn't make any sense. You can't do it. So we have this problem of fundamentally, how are we even going to think of derivatives? We're going to build up to that. Different approaches that you can take. It's actually various different kinds of derivatives. We're going to see like 5 or 6. I've forgotten. I could count at some point. But there's a significant handful of different kinds of derivatives that apply in different settings in different ways with different motivations. But arguably there is a sort of a fundamental point of view on what a derivative is. And a derivative, as it turns out, is an object of linear algebra. Something called the linear transformation. So we're going to need to define linear transformations, and we're going to need to develop some tools for manipulating linear transformations effectively and conveniently. And here we are, linear algebra. Okay. All right. So that said, a quick definition I want to make, and this is just terminology, but I need to define the term linear combination. I'll be using that term linear combination a lot. Let me point to that real quick. A linear combination, if you give me a list of vectors, v1 through vk, a linear combination of those vectors is an expression of this form. It is what you get when each of those vectors might be multiplied by some scalar, and then you add up those results. So this is just a definition. A sum of scalar multiples of a list of vectors. This expression comes up surprisingly often, so often it needs to have a name. The name we use is linear combination of those vectors. Right? So like I say, just terminology. Argument could be made. This is just flash forward to math 216, 221, 218, whatever you're going to take. Could be argued that linear combination is the sort of cornerstone fundamental construction of all of linear algebra. So anyway, it's a good idea. Okay. We're going to need it certainly to define what we're about to define here. I'm going to define something called a linear transformation. Real quick, this is a scary looking little expression here. Let me just point out all this is saying. I just want to point out what a multivariable function is. A multivariable function is a function that has multiple input variables, and of course it might have multiple output variables. If it does, hypothetically, if it does have multiple output variables, notice that each one of those output variables is itself a function of the same input variables that the original function is. So I'm just kind of expanding and breaking down. Let's remind ourselves, what is a multivariable function? Okay. And with that in mind, here's the definition of a linear transformation. I'll do it like this. Linear transformation. It's a multivariable function that has these two seemingly innocent little properties. And let me zoom in so I can focus on these. It needs to be true that if you add two input values, that needs to result in the addition of the corresponding output values. So add before the function, add after the function, cool, you get the same answer either way. It also needs to be true that if you scalar multiply before you plug into the function, the result needs to be to simply scalar multiply the output value of the function. So these are nice properties. These are algebraically convenient when they happen. Most functions don't do this. Right? Square root doesn't do it. Magnitude doesn't do it. Right? Lots of functions just do not behave like this. Some functions do. Every so often, you have a function that has these two properties. And it turns out you can do great things with this. And we're going to study this in more detail next time. We're out of time now. We pick up here on Thursday. Okay, stick around for a moment for homework to be returned, if you will, and I'll